So thank you very much for organizing this event. It's especially, as Burkhard already mentioned, especially at this time when there is a war around and you are still doing beautiful science. I think it's really amazing. Thank you very much, guys, for organizing it. So I will talk about activities which we do very much close in collaboration with a group in Kyiv, with a group of Denis Sheka. Denis will give a talk a little bit later today, and I will try to cover the complementary topic of this geometrically curved magnetic structures, especially from the application point of view. Basically what we are interested in is to fabricate magnetic architectures which have geometric curvature, like thin films or nanowires or ribbons, and try to understand what is the change in magnetic responses or magnetoresistive or magnetoelectric responses due to curvature. One has to tell from the very beginning that the activities on curvature effects in magnetism is only one of the topics which are going on at the moment in condensed matter physics. And if you are interested in what people are doing with geometric curvature for superconductors, semiconductors, 2D materials, or topological insulators, one can simply have a look in the available literature, like simply cite this review paper, but there are definitely other sources. In my talk, I will focus primarily on magnetism, and I will start with a little bit of fundamentals. Without overlapping too much with the talk of Denis, I would like to acknowledge that the development of curvilinear magnetism started very beautifully as a collaboration between the group in Kyiv and also a group in Germany, in Dresden. And this collaboration work already for more than a decade with a very nice outcome. So this is a slide which is based on the original work of Yuri Gaididei. He unfortunately passed away recently, but I would like to simply show his equations for this event. So for my talk, it's very important simply to have the outcome of this analysis. So if you will have a geometric curvature in any kind of magnetic material, ferromagnet or antiferromagnet, geometric curvature will provide you with two effects. And one effect is its emergence of anisotropy response, and another one is induced chiral responses. So these induced effects are not related to the band structure modification. This is an effect which are related purely to the geometry, the change of the geometry of magnetic thin film, for example. What is important that the curvature induced chiral interaction, which in this case comes from exchange interaction, is linear in curvature, and it means that this effect is relatively strong, which allows you to even observe it. And this is a work of Alexei Volkov. He will also give a talk a little bit later in the session. And you can quantify this effect. So even in symmetric stacks of centrosymmetric materials, like, for example, permalloy, you can have a very strong Dzaloshinsky-Murie interaction-like effect at the apex of geometrically curved stripe, like in this case, it's a parabola, which is as strong as you have in, for example, very precisely engineered out-of-plane magnetized cobalt-based asymmetric sandwiches for skyrmion research. This is already a very interesting tuning knob, which material science or physics community can obtain if you play with geometry. So you can induce rather strong chiral responses by tailoring the geometry of magnetic thin films. You can use the same knowledge of possibility to impose the Dzaloshinsky-Murie interaction to create skyrmions, like this solitonic type of excitations, based on materials with extreme curvature radii, as it's shown here. This is also work of two Ukrainian scientists, Volodymyr Kravchuk and Alexander Pilipovsky, where you can nicely see that there will be possibility to create such kind of solitonic objects in geometrically curved magnetic thin film. This is something which I find extremely beautiful on a fundamental side, because the new framework which you have now in hand with a curvilinear magnetism, it allows you to understand physics better in a way deeper understand the physics. And in this case, you can have new means to discover new effects. Even in classical micromagnetism, this is a work of Denis Shek, a very recent one, where he predicted the presence of non-local chiral symmetry breaking effect in such kind of geometrically curved magnetic thin films. And there was a couple of years of very intense collaboration between the groups to understand what is a physical consequence of such kind of non-local chiral symmetry break. And this is now, like this year, we have a very interesting achievement, which will be discussed by Alexei Volkov in his talk, that even in such kind of standard, very classical objects like magnetic vortex state, where you have a circulation of magnetization in a magnetic nanodot, you can induce two magnetochiral properties, like one is a chiral properties of magnetic vortex texture, and also the change of the twist of magnetic vortex string, which is actually quite an interesting physical observation, but we still are lacking because such kind of structures do not exist at the moment, like before they didn't exist. Therefore, even the application potential of having two magnetochiralities in one, or magnetochiral properties in one magnetic object, is not obvious. So we are still even searching for potential application directions for this type of structures. If you mention about potential applications, so this is exactly where the link to the my actual talk is, that where you understand the physics, the fundamentals of magnetic domain spinning in such kind of geometrically curved structures, how the resistive properties of these thin films are changing, you can think about applying them for applications in, let's say, electronics, which is dynamically deformable. You usually address this as, for example, printed electronics or flexible electronics or on-skin electronics. Such kind of electronics where magnetic thin film, upon use of this thin film, will be dynamically deformed. And this is exactly what I will try to introduce to you in next couple of minutes, where I will tell you how we fabricate so-called skin-conformal magnetoelectronics, thin films on polymeric foils, and especially I will try to discuss why we are trying to fabricate this type of films. So basically the motivation, like a justification for these activities, is very, very important for us. This is a standard application range of different magnetic materials and in magnetism in general. Basically, you have magnetic compasses in your smartphones, for example. You use magnetic field sensors in hard disk drives as reed switches. Usually, these magnetic field sensors are such kind of packaged elements, which are shown here in the center of the slide, couple of millimeters large, about 1 millimeter thick. And this is a very successful technology. One has to really tell that this is one of the mainstream technologies for over, I don't know, about 100 years in many different industries. What people are doing for last couple of decades, let's say 20, 30 years, they're trying to move away from the rigid substrates and explore flexible substrates. It's not very new type of research, as I said, about 30 years, but very recently people started to work with very thin foils. So instead of using 1 millimeter thick silicon substrate, you use, let's say, 1 micrometer thick polymeric substrate. And this gives you very interesting advantages of, for example, your magnetic field sensors, this patterned stripes, what you can see in the image, they become flexible, they become very thin, and what is very important, and I think this is the most important ingredient here, they become lightweight. They are very, very light, and now you can put these sensor devices on very unusual objects, like, for example, you can put them on a soap bubble, you can put them on your skin and use it for on-skin electronics, because these devices, because of extreme thinness and lightness, they do not disturb your skin performance, right? This is a technology already. If you think about a little bit thicker foils, like let's say 100 micrometer or something like that, you will be able to fabricate these sensors on, like in a batch process, like you do it industrially on foils with a size of, let's say, 300 millimeter. It's a standard microelectronic wafer scale, which you can use with a very interesting advantages. So instead of using wafers, you can use optically transparent substrates, like polymers are typically optically transparent. And now you can fabricate your sensors which will be not only flexible and magnetosensitive, but they will be also optically transparent. And this you can use, for example, for interactive electronics where optical transparency is important. For example, you just want to put it on a window or integrate it on a display of your cell phone or computer. What is important here that you can fabricate the sensors on a large area, polymeric foils, and the performance of these devices, like even very demanding giant magnetoresistive sensors, will be very similar to those prepared on rigid silicon wafers. This is exactly what I mean with the technology already. These topics are quite interesting for students because it's scientifically appealing. It's interesting for students because you need to involve many different expertises. Like what you see here is a standard workflow which you have to do as a PhD student in this field or researcher in this field, where you have to use thin film deposition on unusual substrates like polymers. You have to do lithography, you have to do structuring, you have to measure magnetoelectrical performance, like you measure change of electrical resistance in the magnetic field, absolutely standard measurements for magnetoresistive performance, but your sensors are mechanically flexible. They are prepared on, let's say, very thin polymeric foils, and therefore large majority of your work is dedicated to understand also the mechanical stability of the sensors. When is a resistance becomes changing, for example, when you bend your sensor, when the magnetoresistance starts changing when you bend your sensor, or you start to do such kind of repetitive bending test where you simply bend your sensor for many times to predefined bending radii, and you see what is actually happening. The idea here of all this optimization is, of course, to have a sensor which is a sensor of magnetic field, but not a sensor of strain, which is also exciting topic, but it's something which you try to avoid if you want to make, let's say, skin conformal magnetoelectronics. And if you are successful, like for example, here is demonstrated, you can apply your sensor to the skin. Like for example, you can put it on a finger, you can put it on a prosthetic finger, you can put it on different type of devices in order to realize human-machine interfaces, which are based now on interaction with magnetic fields. This is something which is very unusual for humans because now you bring into interaction something which people do not use usually, the magnetoreception. This is an artificial type of magnetoreception which you can use for smart home applications just to improve the interactivity with devices. You can also go into something which is a little bit more visionary, maybe to virtual reality applications, to augmented reality applications, where you try to use magnetosensitive skins in order to interact with virtual objects. These objects you cannot really touch, but you can, for example, still interact with them in a touchless way, for example, by using gestures, right? So this is a very interesting complement to the conventional immersive VR, where you use VR goggles, for example, and gestures to perform fine motoric type of activities. So that's what you can do already at the moment with such kind of magnetosensitive skins. Where I see a very huge potential of where this type of activities can impact the development of material science and also applications, it's a possibility to use such kind of flexible devices, but in a form of printed sensors. So instead of going from silicon wafers to polymers, you make another step. And now you tell, look, I want to go away from thin films, and I want to fabricate some kind of feedstock material. Like feedstock in this respect, it's a powder, let's say magnetosensitive powder, which you have to mix somehow with a binder, polymeric binder, to create a paste. And this paste you can print using screen printer, dispenser printing, or simply painting on different types of substrates. And this is something which is very beautiful conceptually, because now you can go away from the standard thin film fabrication technologies, which make magnetism community very much unique. You can simply offer the magnetic functionalities now to chemists or material scientists which do not have, let's say, €1 million in order to invest in a deposition device to fabricate giant magnetoresistive sensors. Now, in principle, everybody who can process polymers or composites can fabricate high-performance magnetic field sensor. And this is really beautiful freedom what you can get with it, because now you can print. This is a commercial dispenser printer, nothing very special. You can print magnetic sensitive stripes. You can process them in case you need to sinter them. Beautiful material science behind all these things, like adhesion of materials, different substrates. You can print now contacts to them. You can integrate your sensors in any type of very, very complex even circuit, because now you can print your layout. You don't need to do lithography. You don't need to worry about all the vacuum facilities which should be provided. You just use your printer, multi-material print, in order to fabricate sensors of any type of layout. And this is actually quite high performance sensors. If you will have a look at the bottom of the slide, you see characterization of these sensors. In this case, we use bismuth. It's not really magnetic material, but bismuth, it's a very special type of material. It's a higher order topological insulator. It has very interesting band structure, which allows you to have quite large magnetoresistive effect. And what is interesting about this effect, it's a linear magnetoresistive effect. It means that if you will increase a field, the magnetoresistance at high fields will behave linearly. Like, for example, we know that these sensors do not saturate their response up to 40 Tesla. 40 Tesla, when I tell 40 Tesla, I mean that at HCDR, we have another large-scale facility to ion beam center, which works with high magnetic field labs. So therefore, if in the audience, there is somebody who wants to work also with high magnetic fields, you can easily contact us, me or Stefan, and we can make a link with such kind of beamline scientists. What is interesting about it, that even printed magnetic field sensor can reveal a resistance change in a magnetic field of a couple of Tesla of several 1000% at low temperatures. And this is way higher than any kind of magnetoresistive effect in giant magnetoresistive or even tunneling magnetoresistive devices. And this is all done on polymers and on printed technology. Idea behind it is very interesting, especially for material scientists, because here you have to really apply all the knowledge about materials and the composites and percolation effects, electrical percolation, mechanical stability of those composites. Imagine you have somehow a powder, which is magnetosensitive, can be thin film fabricated GMR flakes, or you simply buy or fabricate magnetic particles. You put them in a binder. And here starts already a lot of interesting chemistry and material science, because the binder has to be appropriately adjusted in order to assure adhesion, of course, assure electrical percolation and processability of this material. In our case, we work, for example, with 3-block copolymers like PBS in this notation, and which gives very interesting possibilities to put these devices even by printing to ultra-thin foils. Why is it interesting? Well, it's interesting because the heavy duty of magnetic field sensors, which you are buying them, it's a conventional switch application. Like switch can be mechanical, it can be electrical, like transistors, for example, it's electrical switches. And in magnetism, you also have spin valves, for example, it's a magnetic switches. So such kind of devices are easy to fabricate, let's say, in standard rigid electronics. But if you want to have something printed, you need, of course, a very special type of materials which can allow you to fabricate conventional printed magnetoresistive switches. And this is something which you can do now if you will have such kind of composites. This is a collaboration with a group of Mykola Bilnichenko. He's actually also like some time back graduated from physics faculty of Shevchenko University. Now he's also in Dresden. And what is interesting here, you can print magnetic field sensors with screen printer. You can, of course, use magnetic field sensors as a switches, because if you will expose them to magnetic fields of this rotating permanent magnets, you will change resistance of the sensor, which can in turn change of the logic levels in the system, and, for example, switch off or switch on the lamp, which is shown here in this advertisement application, right? So such kind of magnetic printed magnetoelectronics you can use, for example, for printed interactive energy efficient electronics. And this is something which is very interesting. It gives you very interesting possibilities also, because as you can imagine, you can use printing facilities to print millions, billions of sensors with screen printer. Just for reference, you can print, let's say, 1 billion of sensors in about 1 month. The total number of magnetic field sensors which are produced per year by the entire world is in range of 10 billion sensors. So in principle, you can simply use printing technologies to complement all these other activities without any problem. And this is with a single facility, right? So a single lab scale facility. So it's a huge potential behind this technology. What gives you a possibility to work with composite? It's you come very close to skin. Think about your skin. If you will, for example, make a small cut, like on the skin, there will be, of course, a small wound, but it will self-heal. Like self-healing possibility of our skin is essential for our everyday life. If you will think about wafer, just think about wafer and you break the wafer. The wafer, if it's broken, cannot be collected back because physicists will explain you that there is a thermodynamic and entropy and everything is changing. And this have to be then broken. You cannot repair it. Our skin is doing exactly the same entropy and everything, but it self-heals. Now you can do very interesting trick. You can use polymers which have so-called dynamic bonds. If you have a highly dynamic bonds, you can realize such kind of composite. PBS, polyboroxyloxane. This is a material which is a standard material which has exactly the properties of dynamic bonds. You can reinforce it with PDMS, it's a synthetic rubber, polydimethylxyloxane, and put the magnetic content like permalloy particles. And what you see here, it's a composite which looks like a slurry a little bit, and it has like a crack. You can simply cut the crack through this composite. And now what you see in a real time, this crack is just healing. It's healing mechanically, but at the same time, what you cannot see on this movie, it's healing electrically. It works like this. So if you will have 3 components here, imagine you have a sensor which is integrated, or sensor, basically a conductor, which is integrated in a circuit with a lamp. And this lamp, it's a LED, which is just, oops, excuse me, it has to one. An LED which can be, of course, simply disconnected from power if you will cut the conducting path. Now, if you would not have self-healing possibility for this device, the lamp would not go on. So now what you can do, you can cut this device many times. This is now a loop in a movie, but you can repeat it over and over again, simply by damaging the conducting path and then repairing it by bringing this magnetic composite to an alternating magnetic field of this electromagnet. So at the big black thing in the center of the screen, this is the electromagnet which provides a couple of millitesla, a couple of hertz magnetic field for self-healing. And as I said, you can do it beautifully many times. You can cut it, you can repair it, you can even repair it when it's in water. So just imagine about electronics which you have integrated in a textile, and even if it's broken when you wear it, which can happen with wearable electronics, upon washing and using such kind of a very weak, gentle magnetic field, alternating magnetic field processing, you can recover your sensor. And not only mechanically, but also magnetoresistive performance will be recovered very well. Okay, now I think I'm already pretty much advanced in my time. Instead of summary, I would like to tell that probably this is the most important conclusion. You can use curvature as a new mean in material science. You have a new possibility to design magnetic responses like chiral or anisotropic by tailoring geometry of thin film. This is very different compared to material screening approach, where you have to change composition, where you have to change, for example, fabrication conditions, strain, for example, or other means which allow you to get, for example, properties which you need, like Dzielaszynski-Marie interaction of certain strengths. In this case, you have a complementary tuning knob to realize such kind of interactions. On the application side, you have a very interesting transition, which is going from rigid electronics to such kind of flexible electronics. Here, as I already mentioned, we are more or less advanced. We have already a technology which can be purchased, so people can purchase such kind of flexible devices. The interesting part of the next development level, it's a possibility to have printed electronics, because this electronics is working with composites. It allows you to use basically any printer, standard printer, or even 3D printer. You can do additive manufacturing in order to fabricate magnetic field sensors and integrate it in other printed structures, with very interesting advantages of being self-healable and even eco-sustainable. This topic I will simply not cover in this talk, but we can discuss on this afterwards. If you have students who are interested or they have entrepreneurial spirit, they are very good scientists, but they want to go and develop these technologies further as a commercial products, they can easily do it, because now you have a very interesting new technology, flexible or printed electronics, magnetoelectronics. Well, let's simply create a spin-off and try to commercialize it. And this is exactly what people are doing. We have fantastic support here in Dresden from the daughter company of HZDR, it's HZDR Innovation, and they support our students in order to do such kind of first steps in technology transfer, which is very, very valuable, of course, for potentially for the career development of our PhD students, master students, or postdocs. If you are not material scientists, but you still like the topic, this is also very interesting, because if you are good in signal processing, let's say electrical engineering, and understand physical concepts of measurement of spin orbit effects and spin transfer torque effects, you will be able also to try to do commercialization activities in a sense that you will try to patent and develop equipment to measure this dynamically bendable magnetic field sensors, trying to cancel all effects which comes from strain effects, and only magnetic field information has to be delivered as an output signal. So such kind of concepts are very, very interesting, and people can become very successful and very unique in their research. I would like to thank you for your attention. Very much happy to be part of this event. If you have questions, we can definitely discuss. I'm also around.